Hi, I hope you're all having a lovely virtual VMSG. My name is Sarah Shi, and I'm a current MPhil student at the University of Cambridge. Today, I'll be presenting on my undergraduate work done at the Mont Doherty Earth Observatory regarding the 2018 eruption at Volcán de Fuego. We're specifically interested in Fuego given the hazards that are associated with unexpected transitions between steady-state, low-level effusive activity and vigorous paroxysmal eruption, last seen during the 2018 VEI-3 eruption that led to major pyroclastic flows, unfortunately causing thousands of fatalities and destruction in surrounding communities. We aim to answer two fundamental questions about the eruption to better understand the system and to inform future monitoring. What triggers these transitions of behavior and what governs the explosivity of eruption? We place a particular focus on accurately estimating and reducing uncertainties in timescales and in volatile measurements. Firstly, we time magma mixing with iron-magnesium diffusion chronometry and olivine. We develop a novel liquid thermometer to reduce uncertainties in temperature and thus in our diffusivities and timescale. Secondly, we constrain magma storage conditions by measuring the volatiles that are contained in olivine-hosted melt inclusions. We determine volatile concentrations with uncertainties with a new MCMC model for fitting baselines to FTIR spectra. We also consider the 2018 eruption in this larger eruptive context by comparing it to the more explosive 1974 VEI-4 eruption, which has been well studied with quantified volatiles and decompression rates. Our ash and lapilli samples for this study were collected off rooftops from the town of Aguas Calientes in the week following the eruption by our collaborators. From these samples, we isolate euhedral crystals of olivine and orient them along the AC or the O10 plane to expose the fast crystallographic axes of diffusion along C for iron-magnesium diffusion and along A for water. We measure iron-magnesium profiles in oriented euhedral olivine crystals along the C and the A axes to deconvolve the effects of growth and diffusion. Here are the shortest and longest length-scale iron-magnesium profiles we measure, represented with Forsterae on the y-axis. These chemical gradients are generated by magma mixing, causing some change in condition, which is then diffusively smoothed over time. And when we model these profiles with an initial condition at the rim, we obtain records of magma mixing that extend from 25 years to just 6 months prior to eruption. The uncertainty and timescales indicated here are based on temperature uncertainties from our new liquid thermometer, calibrated on art composition experiments with an implicit iterative inversion technique, which successively determines best fit model parameters, all while accounting for the inherent uncertainties in experimental and analytical measurements. In Fuego's temperature range of 1,000 to 1,100 degrees Celsius, 1 sigma is 12 degrees, which halves the uncertainty in temperature compared to previously published thermometers. This increase in precision is also accompanied by an increase in accuracy, as we see greater alignment between predicted and experimental temperatures along the 1-to-1 line. This allows us to evaluate absolute timescales and to better compare these with geophysical records. We also find these short length scale reversals that range from about 15 to 40 microns in several olivine profiles measured along the fast axis for growth or diffusion along C and not in the slower A axis in the same crystals. Whether these are related to diffusion or growth or some mixture of the two, these reversals represent some final mixing events in the days to weeks prior to eruption, potentially aligning with the seismic and acoustic unrest recorded in the 2 weeks prior to eruption by Diaz-Moreno et al. In their 2020 Frontiers paper. We not only record the final magma injection and mixing in these small rim profiles, but also, when we plot magma mixing to eruption timescales in these longer length scale profiles on the top, they reflect a similar ramping up of magma mixing to the number of paroxysms shown on the bottom. This is most dominant in the 5 years prior to eruption, where the cumulative paroxysmal count also sees the steepest gradients. These diffusion timescales begin to reveal what happens in the decades to days and weeks before eruption, but we still need to work through how we can understand explosivity at Fuego. We begin to answer this question by quantifying volatile budgets. We measure the volatiles that are preserved in olivine-hosted melt inclusions by FTIR and find a distinct offset in water concentrations. The 2017 samples average about 2.7 weight% water, whereas 1974 averages 4.1. This distinct offset by almost a weight% and a half of water is stark, whereas CO2 entirely overlaps. We can also be confident in this offset despite the difference in analytical technique, with 1974 melt inclusions being measured by SIMS because we develop an MCMC algorithm to fit baselines to FTIR spectra. We assess the fundamental shape and variability in the baseline with a suite of devolatilized melt inclusion spectra from the elutions, with no molecular water and no carbonate. We use principal components analysis to isolate variability in the baseline shape, and from this we generate an MCMC model that then varies the baseline, the principal components accounting for variability in the baseline, and peak heights in this mid-IR range to properly assess volatile concentrations with uncertainties. And over here, you can see some of the variability and potential baselines fit through this MCMC trial run plotted. A few of the 1974 melt inclusions plotted here are also samples we've doubly polished and remeasured by FTIR. A few different processes could generate this offset in water. You could have a drier or different parental melts, enhanced water loss due to CO2 fluxing, or post-entrapment diffusive water loss modifying water contents. We can assess which process is the most likely by looking to non-diffusive volatiles and trace element ratios. And in this space, we see that the 2018 melt inclusions entirely overlap those from 1974 in sulfur and silica content and carry an identical barium-zirconium ratio. The similarity in non-diffusive volatiles, barium-zirconium ratios, and also rare earth elements suggests that these eruptions were sourced from the same parental magma. CO2 fluxing would further deplete sulfur and offset sulfur from CO2, which is not observed. We instead propose that this offset in water was generated by shallow stalling at a depth of around 3.4 kilometers in the months prior to eruption, causing the magma to degas and for the melt inclusions to diffusively lose water, which would begin to enhance extent of crystallization. And this is indeed reflected in the lower rim forsterite compositions in equilibrium with matrix glass for 2018, peaking at 71.3 and offset from 1974 by around 1.5 forsterite units. The potassium content in the matrix glass from 2018 is also enriched by 70% compared to the maximum observed in 1974. Both forsterite and potassium reflect a magma that's undergone increased crystallization and evolution, also increasing magma viscosity for the 2018 eruption. Instead of racing to the surface from 10 kilometers depth in just 10 minutes, as in 1974, the 2018 magma first stalled at around 3.5 kilometers depth, followed by ascent from a shallower depth with a more viscous magma, which would decrease the explosivity of eruption and explain this order of magnitude difference in explosivity. Furthermore, we find that a final injection of magma through recharge or destabilization occurred in the weeks to days prior to eruption, recorded in these short Lengthscale rim reversals. Thank you all for listening, and I look forward to discussion during the conference.